A carbon sink is a natural or artificial reservoir that accumulates and stores some carbon-containing chemical compound for an indefinite period. The process by which carbon sinks remove carbon dioxide from the atmosphere is known as carbon sequestration. Public awareness of the significance of CO2 sinks has grown since passage of the Kyoto Protocol, which promotes the use as a form of carbon offset. There are also different strategies used to enhance this process. The natural sinks are absorption of carbon dioxide by the oceans via physiochemical and biological processes, photosynthesis by terrestrial plants. Natural sinks are typically much bigger than artificial sinks. The main artificial sinks are landfills, carbon capture and storage proposals. Carbon sources include combustion of fossil fuels by humans for energy and transportation. Farmland. There are proposals for improvements in farming practices to reverse this. Kyoto Protocol. Because growing vegetation takes in carbon dioxide, the Kyoto Protocol allows Annex I countries with large areas of growing forests to issue removal units to recognize the sequestration of carbon. The additional units make it easier for them to achieve the target emission levels. It is estimated that forests absorb between 10 and 20 tons of carbon dioxide per hectare each year, through photosynthetic conversion into starch, cellulose, lignin, and wooden biomass. While this has been well documented for temperate forests and plantations, the fauna of the tropical forests place some limitations for such global estimates. Some countries seek to trade emission rights in carbon emission markets, purchasing the unused carbon emission allowances of other countries. If overall limits on greenhouse gas emission are put into place, cap-and-trade market mechanisms are purported to find cost-effective ways to reduce emissions. There is as yet no carbon audit regime for all such markets globally, and none is specified in the Kyoto Protocol. National carbon emissions are self-declared. In the Clean Development Mechanism, only afforestation and reforestation are eligible to produce certified emission reductions in the first commitment period of the Kyoto Protocol. Forest conservation activities or activities avoiding deforestation, which would result in emission reduction through the conservation of existing carbon stocks, are not eligible at this time. Also, agricultural carbon sequestration is not possible yet. Storage in terrestrial and marine environments. Soils. Soils represent a short to long-term carbon storage medium, and contains more carbon than all terrestrial vegetation and the atmosphere combined. Plant litter and other biomass including charcoal accumulates as organic matter in soils, and is degraded by chemical weathering and biological degradation. More recalcitrant organic carbon polymers such as cellulose, hemicellulose, lignin, aliphatic compounds, waxes and terpenoids are collectively retained as humus. Organic matter tends to accumulate in litter and soils of colder regions such as the boreal forests of North America and the taiga of Russia. Leaf litter and humus are rapidly oxidized and poorly retained in subtropical and tropical climate conditions due to high temperatures and extensive leaching by rainfall. Areas where shifting cultivation/and-burn agriculture are practiced are generally only fertile for 2 to 3 years before they are abandoned. These tropical jungles are similar to coral reefs in that they are highly efficient at conserving and circulating necessary nutrients, which explains the lushness in a nutrient desert. Much organic carbon retained in many agricultural areas worldwide has been severely depleted due to intensive farming practices. Grasslands contribute to soil organic matter, stored mainly in their extensive fibrous root mats. Due in part to the climatic conditions of these regions, these soils can accumulate significant quantities of organic matter. This can vary based on rainfall, the length of the winter, winter season, and the frequency of naturally occurring lightning-induced grass fires. While these fires release carbon dioxide, they improve the quality of the grasslands overall, in turn increasing the amount of carbon retained in the humic material. They also deposit carbon directly to the soil in the form of char that does not significantly degrade back to carbon dioxide. Forest fires release absorbed carbon back into the atmosphere, as does deforestation due to rapidly increased oxidation of soil organic matter. Organic matter in peat bogs undergoes slow anaerobic decomposition below the surface. This process is slow enough that in many cases the bog grows rapidly and fixes more carbon from the atmosphere than is released. Over time, the peat grows deeper. Peat bogs hold approximately 1/4 of the carbon stored in land plants and soils. Under some conditions, forests and peat bogs may become sources of CO2, such as when a forest is flooded by the construction of a hydroelectric dam. Unless the forests and peat are harvested before flooding, the rotting vegetation is a source of CO2 and methane comparable in magnitude to the amount of carbon released by a fossil fuel power plant of equivalent power. Regenerative agriculture. Current agricultural practices lead to carbon loss from soils. It has been suggested that improved farming practices could return the soils to being a carbon sink. Present worldwide practices of overgrazing are substantially reducing many grasslands' performance as carbon sinks. The Rodale Institute says that regenerative agriculture, if practiced on the planet's 3.6 billion tillable acres, could sequester up to 40% of current CO2 emissions. They claim that agricultural carbon sequestration has the potential to mitigate global warming. When using biologically based regenerative practices, this dramatic benefit can be accomplished with no decrease in yields or farmer profits. Organically managed soils can convert carbon dioxide from a greenhouse gas into a food-producing asset. In 2006, U.S. carbon dioxide emissions, largely from fossil fuel combustion, were estimated at nearly 6.5 billion tons. If a 2,000 per year sequestration rate was achieved on all 434 million acres of cropland in the United States, nearly 1.6 billion tons of carbon dioxide would be sequestered per year, mitigating close to 1/4 of the country's total fossil fuel emissions. Oceans. Oceans are at present CO2 sinks, and represent the largest active carbon sink on Earth, absorbing more than 1/4 of the carbon dioxide that humans put into the air. The Southern Ocean absorbs about 40% annual global CO2 emissions through winds, currents and eddies that transport warm and cold water around the ocean. The Solubility pump is the primary mechanism responsible for the CO2 absorption by the oceans. The biological pump plays a negligible role, because of the limitation to pump by ambient light and nutrients required by the phytoplankton that ultimately drive it. Total inorganic carbon is not believed to limit primary production in the oceans, so its increasing availability in the ocean does not directly affect production. However, ocean acidification by invading anthropogenic CO2 may affect the biological pump by negatively impacting calcifying organisms such as coccolithophores, foraminifers and pteropods. Climate change may also affect the biological pump in the future by warming and stratifying the surface ocean, thus reducing the supply of limiting nutrients to surface waters. A study from 2008 claims that CO2 could increase primary productivity, particularly in eelgrasses in coastal and estuarine habitats. This postulate, however, has yet to be proven. In January 2009, the Monterey Bay Aquarium Research Institute and the National Oceanic and Atmospheric Administration announced a joint study to determine whether the ocean off the California coast was serving as a carbon source or a carbon sink. Principal instrumentation for the study will be self-contained CO2 monitors placed on buoys in the ocean. They will measure the partial pressure of CO2 in the ocean and the atmosphere just above the water surface. In February 2009, Science Daily reported that the southern Indian Ocean is becoming less effective at absorbing carbon dioxide due to changes to the region's climate, which include higher wind speeds. On longer timescales, oceans may be both sources and sinks. During ice ages, CO2 levels decreased to 180 ppmv, and much of this is believed to be stored in the oceans. As ice ages end, CO2 is released from the oceans, and CO2 levels during previous interglacials have been around 280 ppmv. This role as a sink for CO2 is driven by two processes, the solubility pump and the biological pump. The former is primarily a function of differential CO2 solubility in seawater and the thermohaline circulation, while the latter is the sum of a series of biological processes that transport carbon from the surface euphotic zone to the ocean's interior. A small fraction of the organic carbon transported by the biological pump to the seafloor is buried in anoxic conditions under sediments and ultimately forms fossil fuels such as oil and natural gas. At the end of glacials, with sea level rapidly rising, corals tend to grow slower due to increased ocean temperature, as seen on the Showtime series Years of Living Dangerously. The calcium carbonate from which coral skeletons are made is just over 60% carbon dioxide. If we postulate that coral reefs were eroded down to the glacial sea level, then coral reefs have grown 120 meters upward since the end of the recent glacial, enhancing natural sequestration. Forests are carbon stores, and their carbon dioxide sinks when they are increasing in density or area. In Canada's boreal forests, as much as 80% of the total carbon is stored in the soils as dead organic matter. A 40-year study of African, Asian, and South American tropical forests by the University of Leeds shows tropical forests absorb about 18% of all carbon dioxide added by fossil fuels. Truly mature tropical forests, by definition, grow rapidly, as each tree produces at least 10 new trees each year. Based on studies of the FAO and UNEP, it has been estimated that Asian forests absorb about 5 tons of carbon dioxide per hectare each year. The global cooling effect of carbon sequestration by forests is partially counterbalanced in that reforestation can decrease the reflection of sunlight. Mid to high latitude forests have a much lower albedo during snow seasons than flat ground, thus contributing to warming. Modeling that compares the effects of albedo differences between forests and grasslands suggests that expanding the land area of forests in temperate zones offers only a temporary cooling benefit. In the United States in 2004, forests sequestered 10.6% of the carbon dioxide released in the United States by the combustion of fossil fuels. Urban trees sequestered another 1.5%. To further reduce U.S. carbon dioxide emissions by 7%, as stipulated by the Kyoto Protocol, would require the planting of an area the size of Texas every 30 years. Carbon offset programs are planting millions of fast-growing trees per year to reforest tropical lands, for as little as 10 cents per tree. Over the typical 40-year lifetime, 1 million of these trees will fix 1 to 2 megatons of carbon dioxide. In Canada, reducing timber harvesting would have very little impact on carbon dioxide emissions because of the combination of harvest and stored carbon in manufactured wood products along with the regrowth of the harvested forests. Additionally, the amount of carbon released from harvesting is small compared to the amount of carbon lost each year to forest fires and other natural disturbances. The Intergovernmental Panel on Climate Change concluded that a sustainable forest management strategy aimed at maintaining or increasing forest carbon stocks, while producing an annual sustained yield of timber fiber or energy from the forest, will generate the largest sustained mitigation benefit. Sustainable management practices keep forests growing at a higher rate over a potentially longer period of time, thus providing net sequestration benefits in addition to those of unmanaged forests. Life expectancy of forests varies throughout the world, influenced by tree species, site conditions and natural disturbance patterns. In some forests carbon may be stored for centuries, while in other forests carbon is released with frequent stand-replacing fires. Forests that are harvested prior to stand-replacing events allow for the retention of carbon in manufactured forest products such as lumber. However, only a portion of the carbon removed from logged forests ends up as durable goods and buildings. The remainder ends up as sawmill byproducts such as pulp, paper and pallets, which often end with incineration at the end of the life cycle. For instance, of the 1,692 megatons of carbon harvested from forests in Oregon and Washington from 1900 to 1992, only 23% is in long-term storage in forest products. Oceans. One way to increase the carbon sequestration efficiency of the oceans is to add micrometer-sized iron particles in the form of either hematite or melantoride to certain regions of the ocean. This has the effect of stimulating growth of plankton. Iron is an important nutrient for phytoplankton, usually made available via upwelling along the continental shelves, inflows from rivers and streams, as well as deposition of dust suspended in the atmosphere. Natural sources of ocean iron have been declining in recent decades, contributing to an overall decline in ocean productivity. Yet in the presence of iron nutrients, plankton populations quickly grow or bloom, expanding the base of biomass productivity throughout the region and removing significant quantities of CO2 from the atmosphere via photosynthesis. A test in 2002 in the Southern Ocean around Antarctica suggests that between 10,000 and 100,000 carbon atoms are sunk for each iron atom added to the water. More recent work in Germany suggests that any biomass carbon in the oceans, whether exported to depth or recycled in the euphotic zone, represents long-term storage of carbon. This means that application of iron nutrients in select parts of the oceans at appropriate scales could have the combined effect of restoring ocean productivity while at the same time mitigating the effects of human-caused emissions of carbon dioxide to the atmosphere. Because the effect of periodic small-scale phytoplankton blooms on ocean ecosystems is unclear, more studies would be helpful. Phytoplankton have a complex effect on cloud formation via the release of substances such as dimethyl sulfide that are converted to sulfate aerosols in the atmosphere, providing cloud condensation nuclei, or CCN. But the effect of small-scale plankton blooms on overall DMS production is unknown. Other nutrients such as nitrates, phosphates, and silica as well as iron may cause ocean fertilization. There has been some speculation that using pulses of fertilization may be more effective at getting carbon to ocean floor than sustained fertilization. There is some controversy over seeding the oceans with iron. however, due to the potential for increased toxic phytoplankton growth, declining water quality due to overgrowth, and increasing anoxia in areas harming other sea life such as zooplankton, fish, coral, etc. Soils. Since the 1850s, a large proportion of the world's grasslands have been tilled and converted to croplands, allowing the rapid oxidation of large quantities of soil organic carbon. However, in the United States in 2004, agricultural soils including pasture land sequestered 0.8% as much carbon as was released in the United States by the combustion of fossil fuels. The annual amount of the sequestration has been gradually increasing since 1998. Methods that significantly enhance carbon sequestration in soil include no-till farming, residue mulching, cover cropping, and crop rotation, all of which are more widely used in organic farming than in conventional farming. Because only 5% of U.S. farmland currently uses no-till and residue mulching, there is a large potential for carbon sequestration. Conversion to pastureland, particularly with good management of grazing, can sequester even more carbon in the soil. Terra preta, an anthropogenic, high-carbon soil, is also being investigated as a sequestration mechanism. By pyrolysing biomass, about half of its carbon can be reduced to charcoal, which can persist in the soil for centuries, and makes a useful soil amendment, especially in tropical soils. Savanna-controlled burns on far north Australian savannas can result in an overall carbon sink. One working example is the West Arnhem Fire Management Agreement, started to bring strategic fire management across 28,000 square kilometers of Western Arnhem land. Deliberately starting controlled burns early in the dry season results in a mosaic of burnt and unburnt country which reduces the area of burning, compared with stronger, late dry season fires. In the early dry season there are higher moisture levels, cooler temperatures, and lighter wind than later in the dry season. Fires tend to go out overnight. Early controlled burns also results in a smaller proportion of the grass and tree biomass being burned. Emission reductions of 256,000 tons of CO2 have been made as of 2007.